You probably interact with them a dozen times a day, and maybe don't even realize it. From the camera on your phone to the shows recommended to you online. But what exactly are artificial neural networks? How do these digital brains actually work? Well, we're going to break it all down.
The whole idea is really inspired by the most complex machine we know of, the human brain. So on the left, you've got a biological neuron, which is just nature's master processor. And on the right, that's its digital twin. The big question that started all of this was, hey, if we can build a computer that mimics how our own brains learn, what could it possibly be capable of?
So here's our game plan. We'll start by taking apart that digital brain cell. Then we'll see how they all connect together to form these incredibly powerful networks. After that, we'll get into how they actually learn, and finally, we'll see them in action with some real-world examples.
All right, let's start with the absolute basics. I'm talking about the single fundamental building block of any neural network, the artificial neuron. If you can wrap your head around this, you're halfway to understanding everything else.
This little guy is often called a perceptron, and really, you could just think of it as a tiny decision maker. It looks at a few different pieces of information, its inputs, does a really quick calculation, and then just spits out a single answer. It might sound simple, but it is the foundation for everything.
So how does it know which inputs matter and which ones don't? That right there is where weights come in. A weight is literally just a number that tells the neuron how important a connection is. If you have a high weight, the neuron pays a lot of attention to that input. A low weight, it pretty much ignores it. And the entire learning process we're going to talk about, it's really just the network's journey to find the absolute perfect set of weights for whatever job it's trying to do. Okay, so after the neuron adds up all its weighted inputs, it sends that total through one last thing, an activation function. Think of this as the final gatekeeper. It's the bouncer at the door that decides if the signal is strong enough for the neuron to fire and pass a message along. And this is absolutely crucial. Without it, a network could only learn super simple straight line patterns. It's this function that lets it understand the messy, complex relationships of the real world.
Now, one neuron is cool and all, but the real magic, the part that's so fascinating, happens when you stop thinking about just one and you start connecting thousands or even millions of them together. That's how we go from a simple little decision maker to a full-on artificial brain.
So a typical network has a pretty straightforward structure. First up, you have the input layer. That's just the raw data you're feeding it, say, the pixels of an image. That data then flows into the hidden layers, and these are the real workhorses, where all the heavy lifting and complex pattern recognition happens. And finally, all that information arrives at the output layer, which gives you the final answer, like, yep, that's a cat, or that house is worth $500,000.
It's also kind of helpful to see where neural networks fit into the bigger picture. So they're a huge part of machine learning, which itself is a slice of the much broader field of artificial intelligence. And when you hear that buzzword, deep learning, that just means we're talking about neural networks with lots and lots of hidden layers, making them really deep.
Okay, so we've got this network of neurons, all with their own weights. But how does it actually learn? How does it figure out what the right weights are supposed to be? Well, it's really a process of practice, getting feedback, and making constant adjustments. A lot like how we learn anything.
The whole training process is actually very systematic. First, you split up your data. You use one chunk, the training set, to actually teach the model. That's the study material. Then you use a validation set to check how it's doing, kind of like a practice quiz. You keep training it and testing it on that quiz, tweaking things until it performs well, and only then do you bring out the final unseen test set, which is basically the final exam. Now, this code here describes a super common and critical problem you run into during training. At first, everything looks great. The error goes down on both the stuff the network is training on and the new stuff you're testing it with. But then, notice what happens. The training error keeps on falling, but the validation error, the error on new data, it starts to creep back up. So what in the world is going on here?
This is a classic case of something called overfitting. It's what happens when the model stops learning the general rules and starts, memorizing the specific examples you fed it, including all the weird noise and quirks in that data. It's just like a student who memorizes all the answers to the practice quiz but doesn't actually understand the material. Sure, they'll ace the practice quiz, but they're going to bomb the final exam.
So, when you get right down to it, the whole goal of training is to find that one perfect set of weights, the one that gives you the lowest possible error. Imagine you're in a huge, hilly landscape, and your job is to find the absolute lowest point. The goal is to find the global minimum, the deepest valley there is, without getting tricked and getting stuck in a local minimum along the way, which is a spot that seems pretty good but isn't the best one out there.
Okay, all this theory is great, but let's make it a little more real. Let's look at how these networks are actually put to work, starting with a simple logic puzzle and scaling all the way up to powering massive industries.
So, a classic test for any budding neural network is something called the XOR problem. The rule is super simple, as you can see in the table. The output is 1 if the two inputs are different, and 0 if they're the same. Now that sounds easy, right? But here's the catch. Try to draw a single straight line to separate the ones from the zeros. You literally can't do it. This is what's called a non-linear problem, and it's a perfect job for a neural network.
And that right there brilliantly shows why those hidden layers we talked about are so incredibly important. A single perceptron, a single neuron, is totally stumped by XOR. But if you add just one small hidden layer, suddenly the network gains this amazing ability to learn nonlinear patterns, and it can solve the problem no sweat. This is a foundational concept for why they're so powerful.
Now let's scale that idea way, way up. That very same ability to find complex, nonlinear patterns is what lets neural networks power decision intelligence across pretty much every field you can think of. They're what spot fraudulent credit card transactions, predict diseases from medical scans, forecast what products you're going to buy, and optimize shipping routes all over the world.
So, if we're going to sum it all up in one sentence, it's this. Inspired by our own biology, artificial neural networks are systems that learn by constantly tweaking their internal connection strengths, their weights, to get incredibly good at finding hidden patterns in massive amounts of data.
And that really leaves us with a pretty fascinating thought to end on. We've actually done it. We've built digital brains that can learn on their own. The big question we have to ask now isn't how they learn, but what should we be teaching them first? What are the most important problems we want them to solve? Thanks so much for watching.